Hey there and welcome to another LeetCode problem. It's going to be problem number 450, delete node in a BST. So we're given a root node reference in a BST and a key, and we need to delete that node and return the root reference, possibly updated of the BST. So for those of you that don't know, a BST is a binary search tree, meaning all the nodes to the left of a node are smaller than that node, and all the nodes to the right of a node are greater than that node. So you can see like here's a 5, so everything here is going to be smaller than 5. Everything here is going to be bigger and so on. So same thing here. So it's giving us an example of where we try to delete root node number 3. And so when we delete node number 3, it's saying you can place this 4 up here. But another valid solution would also be we delete this 3, then we have a 2 up here, and then we put a 4 over here. Okay. And then also, if we don't find the node, then we just iterate through this tree and we just return the tree back. So let's think of different cases that we can have for deleting a node. So case 1, and let's just actually make this, so case 1, our node has 0 children. So, well, what do we do? Like, let's say we try to delete this node. What do we need to do? Well, we just get rid of it and we update this right pointer to be null, right, or none or something. Okay. Now, case 2, 1 child, which would be like this node, right? This node has 1 child. So that's pretty straightforward as well, right? We just take whatever node this is, we delete it, and then we replace it with the node that it's its child. It's left or it's right, and we just update the whatever this node, so if this is the right, we update this right to be this node. Okay. But what if it has 2 children, right? The most complicated case. So in this case, it's a little bit straightforward, but let's say instead of that, what if our tree looks something like this? Let's use this tree right here, right? So let's say we try to delete the root. Well, what would that look like? So that's the third case, is we have 3 children. 0 children, pretty straightforward, we delete the node. 2 children, or 1 child, we just replace the node with its child. Now the third case is 2 children. So what would we replace it with? Would we replace it with a 3? Would we replace it with a 6? What makes sense? And so the way to delete in a BST, the algorithm for deleting in a BST is you need to take whatever node is this node's successor in this whole tree. And what a successor means is the first node that is greater than this node. So in this example, it would be 6. So what we need to do is we need to change this to a 6. Then we need to delete the 6, and then this can just be a 7. And by the way, so the way we're going to be doing this problem is instead of deleting a node, so instead of just deleting a node, we're going to be actually replacing the node, and then we're going to be recurring down. So for example, let's say we try to delete 5, and we find this node 6 that it's its successor. So we're going to say, okay, we try to delete 5, we find the 6, and we're going to say 6 is a successor. So then we're actually going to replace this value 5 with a 6, and then we're going to call delete on the right subtree of this tree, and then we're going to return that value and make that the right subtree. So if we're here, we try to delete 5, we make this a 6. Now we go down here, we try to delete 6, right? And so it's going to be recursion. So we try to delete 6, same thing. What's its successor? It's going to be 7. So we replace this 6 with a 7. And then we go down here and we try to delete 7. And then finally, when the root has no children, we can't recurse down anymore, so then we just pop off the 7. And then we return none here, we return 6 here, or sorry, we return 7. This would be a value 7. And so we're going to update, if we're trying to delete a node, instead of deleting the actual node, we're just going to change its value to the successor, and then we're going to delete the successor. And we're going to keep recurring down until we can always delete some node that's a leaf node. Now, here we found the 6 quite easily, right? Because it was just the next node. But what about if our tree is like this, right? So our tree is 5, just say 1, Now let's say it's like this. Let's say this is 10. And then we have some other stuff here, like 8, 7, 9, 12, let's say. Okay, well, what about in this case? It's not just going to be, the successor node of this 5 isn't just the nodes to its right, right? It's not this node. So in order to find the successor, what you actually need to do is you need to go 1 to the right. So we're going 1 to the right. And then you need to go all the way to the left from where you're at, and that's going to give you the successor. So we go to this 10, and we say while this node is not empty, we just go left, and so the successor of 5 is actually going to be 7. So then we place the value 7 in here, and then we just call delete on this node with 7. So it would try to call delete on this node with 7, and clearly this is not. Oh, by the way, so the other case is, let's say we're on a node and we're trying to delete like node 7. What we're going to do is we're going to say, okay, well, if this node is not the one we're trying to delete, then we need to recurse down the correct subtree. So if the node is bigger, we recurse right, and if the node is smaller, we recurse left. And so in this case, if we're at 10 here, if this node is 10, then, and we're trying to go 7, so we're going to go left. Is this node 7? No. Okay, we're going to go here. Okay, perfect. We found the 7. It has no children, so we don't need to replace anything. We just delete this node straight away, and then we just return. And so our solution here would be 1, 7, and this should always work out if you go 1 to the right and then all the way to the left, right? So 1, 7, 10, 12, and then here we have an 8 and a 9. So that would be the solution for that, where we did get rid of the 5, but we kind of hacked it, where we replaced its value instead of deleting the node directly. Because if you delete the node directly, it gets really tricky. You have to rearrange the whole tree. So instead, we're just going to replace and keep deleting farther on down. And that's going to be our algorithm. So let's try to code that up. So first of all, we're going to have a helper function. We just call delete. And that's going to be on a node. And we also pass in a key, right? We might be able to just call delete node directly, I think. But let's write this up and then see if we can get rid of the function. So first of all, if the node is none, then there's nothing to delete, but we need to still return. So okay. Now the other cases, remember, are if the key we're looking for is bigger or smaller than what we're trying to delete, right? So then in that case, if key is smaller than node.val, then we just say node.left. And we have to keep reassigning this because, for example, if we're here and our key is 4, we are going to try to delete 4. Or actually, no, here's a better example. So let's say we're like this. Our node is 5, 4, 6. And our key is 4. So we're here. We go left. We delete this 4. Now this becomes none, and we return none. So that's why we need to say the left or the right child equals whatever the return of the function is, because the left or the right child might get updated to none. And so we need to say that. So node.left equals none. Or not none, sorry. It's going to be delete node.left key. So that's going to be that case. Other case is if key is greater than node.val. Same exact thing. Delete. Okay, so this is node.right key. And now the other case is it's this, right? So the last possible case we have is if the node is equal to the value we're trying to delete. And remember, we have multiple cases for that, right? So the first case is if the node has no children. If the node has no children, we can just delete the node straight away. So we can just say if not node.left and not node.right. And remember, this else case means that the key is equal to the node value. So if that's the case, we just return none. That's how we would delete. And then whatever this node got called from would get updated. Its pointer would get updated to none. So we're not really deleting. We're just saying this node is no longer a child of anything. Okay. So that's one case. Now another case is if there is a left and there isn't a right, or if there is a right and there isn't a left. So in that case, if, and remember what we do in that case is we just replace it with that node, right? So if node dot left, yeah. So if node dot left, but we don't want to have two. So and not node dot right, then we just return node dot left, because for example, for this, if we're trying to delete this node, and we're saying the left of this is whatever this returns, we could just return this node right here. And so the left of this 5 will be 2. Okay, so that's that case. Then the other case, if this is the other case, so if node.right and not node.left, then we return node.right. And so the final case is if there are two children, right? Because this is no children, this is the left, this is the right. So here we need to remember we need to go one to the right and then all the way to the left, right? So we can just say cur equals node.right, and then we can say while cur dot next does not equal none, right? So while we can go left, actually this wouldn't be next, this would be left. Okay, so now we went one to the right and all the way to the left. Now what we need to do is we need to get that value, right? And then we need to replace that value. We need to put whatever value that was. So let's say it was a 6. We need to put that into the node that we're at. So node.val equals cur.val. And now remember that the successor is always going to be to the right, assuming we have two parents. So now what we need to do is we need to call delete on this right section, and then we need to delete. So let's say we, in this example, let's say we are trying to delete 5 here. So now we replace this 5 with a 6, and now we need to call delete on this right node with the new value we're trying to delete, which would be a 6. So we're basically taking the value of the next node, putting it in our node, and then just calling delete to delete the next node, instead of actually deleting the node in place. Because like I said, that would be tricky. Like how would you just, if a node has two children and you just delete those pointers, then like it's hard to know what goes there, and it's very hard to keep the same tree structure. Okay, so node.val equals cur.val, then we can just say node.right equals, and then we're going to call this delete function, node.right, and then our new key is going to be, remember we're deleting the node that the value that we just updated this value to. So if this is a 6, we're trying to delete 6 now. Okay, and finally, so we just return the node itself. Now let's think about if we can actually do this. Like, do we even need this delete function, or can we just do this in place? I think we can just do this in place, to be honest. And so instead of this being node, this would be root though. So root, just copy all these. So root. I could do a find and replace, but whatever. So because we are using the exact same, like we have the same thing. We have a node and a key. So cur root. Okay, and then we also need to make sure we bring these back. So. Alright. And then instead of returning node, we return root. Okay, so let's just double check this, and then we're gonna try to submit. So if not node, we return none. If key is less than root.val, this should be fine. If key is greater than root.right, else if not root.left and not root.right, return none. If root.left and not root.right, okay. If root.right and not root.left, return curs root.right, okay. Root.val equals cur.val, root.right. Okay, let's try to run that. Alright, so this should be, and all these delete should be delete nodes, so. Did I miss anything? Oh, right. Okay, so this needs to be self.delete instead. This, I guess, should be root. Okay. Great. All right. Okay, so that worked. So let's try to think about the time and space complexity for this. So, time. Well, what are we doing? We are deleting, but worst case scenario, so once again, this is not a balanced BST, and so if our BST is like this, right, where it's, for example, let's say it's like 1, 2, and so on, just one greater, and then the key we're actually trying to delete would be like maybe this leaf node. In that case, the complexity would be O of n, where n is the number of nodes. But on average complexity, if the BST is more or less balanced, then it's going to be O of log n. So worst case is O of n, average is log n, because any kind of tree iteration to find something is going to be log n if it's balanced, because we are getting rid of half the elements every time. Okay, and space. So it's going to be the same thing. The space is going to depend on the recursive call stack, and so worst case scenario, once again, if we have this linear thing, then the recursive call stack is going to have n recursions, and we're not really returning till we get to the very bottom. So that means same thing, where worst case is going to be O of n, and average is going to be a big O of log n. Alright, so that's it for this problem, and if you like these kind of videos, like and subscribe. It'll help grow the channel, and see you in the next one.